Hello everyone, we'll review the last in-class exercise for energetics, right? So we're looking at the subsection on entropy, entropy change, and Gibbs free energy change, right? So for question 1, okay, we are given some data on carbon disulfide, right? So you are given the enthalpy change of formation, okay, of carbon disulfide in the liquid phase as well as the gaseous phase. And then later on, you are given the standard entropy change of vaporization to be positive 86.5 joules per mole per Kelvin. And then question asks you to comment on the sign of the entropy change. So it is positive. Okay, so I think first of all, we need to define the process, right? So it goes from liquid to gas, okay, and then you notice that it is a positive sign. So what does it tell us, right? So I think it should be relatively obvious, because as you go from liquid to gas, you are looking at the particles being more random, okay, so they have a greater degree of freedom, because as compared to in the liquid phase, although they are not held in fixed position, but they are only free to move around the volume of the container they are being contained in. But of course, it's within the liquid surface. They are still held by significant intermolecular forces of attraction. But once they are in the gaseous phase, they are free to diffuse around whatever system they are being placed in. So for example, if they are in a container, they are free to move around the airspace. If they are in the atmosphere, they are free to diffuse to whatever limits. So they are not really bound by any limit. Of course, it really depends on the space they are given. Yeah. So in general, molecules in the gaseous phase, they are more disordered, okay, and they have a greater degree of freedom. And because of this, there are more ways for particles to be arranged and their energy to be distributed in the gaseous phase as compared to when they are in the liquid phase. Yeah, so that is the general kind of explanation you will need to give whenever you are looking at phase transition, be it from solid to liquid or from liquid to gas. Of course, from solid to liquid, the entropy change, you expect it to be less positive as compared to from liquid to gas. Okay, and then for part B, you are required to calculate the Gibbs free energy change for the conversion of liquid carbon disulfides to gaseous carbon disulfides, and then you are required to deduce which state is more stable at 25 degrees Celsius. Okay, so we'll make use of the equation that has been written earlier on. Yeah, because over here we have defined enthalpy change of formation of liquid CS2. So over here we are looking at this particular arrow. So we are looking at 89.70. Okay, so we are looking at carbon solids, okay, plus a quarter S8 solid. Yeah, so this defines the enthalpy change of formation of liquid carbon disulfide. Okay, so using the same thought process, we can close the loop over here. We are looking at the enthalpy change of formation of gaseous carbon disulfides. This is given to be 117.36. Okay, so you notice that the starting material is the same. Well, I mean, because no matter how you define carbon disulfide, whether it's in a liquid or gaseous phase, when you are defining the enthalpy change of formation, we are looking at the enthalpy change where 1 mole of the respective molecule, whether it's in liquid or gaseous phase, is formed from its constituent elements under standard conditions. So the constituent elements is carbon, which is a solid, and then sulfur, which exists as S8. You can also write it as sulfur as in S. If you cannot remember, that it's S8. Yeah, but the more accurate representation will be S8. Okay, then we can do a quick calculation. Okay, regarding the enthalpy change. So the enthalpy change will be equals to negative 89.70, right, plus 117.36. Okay, so we do a quick calculation, punch the calculator, we are going to get positive 27.66 kilojoules per mole. Okay, so after we have gotten this enthalpy change value, okay, just right, after we've gotten this enthalpy change value, what we're going to do is we're going to write out the Gibbs free energy change. So delta G, okay, at 25 degrees C is equals to delta H, okay, minus T delta S. Okay, so we have gotten the delta H, which is calculated to be 27.66. Okay, minus T delta S, T will be 298 Kelvin, 298. Okay, then for delta S, we must remember one thing: the value we are being given is in joules per mole per Kelvin. So we need to convert it to kilojoules because 27.66 is in kilojoules. So we need to multiply this by 10 to the power minus 3. Okay, so that will be 86.50 multiplied by 10 to the power minus 3. Okay, so this is very important. Okay, and then we punch the calculator, we should be getting plus 1.88 kilojoules per mole. Okay, so you notice the sign, it is a positive sign. So when a Gibbs free energy change is positive, that means that from liquid to gas, it is not a spontaneous process. So therefore, CS2 liquid to CS2 gas, okay, is not a spontaneous process. So that means that external energy is required to effect the conversion. Yeah, so because it's not a spontaneous process, your conclusion is that liquid CS2 is more stable as compared to gaseous CS2. Okay, so that's how you perform the conclusion. So normally when we're looking at a reaction, the delta G is positive, then you expect the reactant to be more stable than the product. If the delta G is negative, the product is more stable than the reactant. Okay, then we'll move on to question 2. Okay, then okay, so over here it's about the extraction of iron from iron ore. So the most common one is hematite. Okay, has a high percentage of iron 3 oxide. So the process is carried out in a blast furnace. So iron ore coke is added, hot air is blown at the bottom, and then limestone is added to convert impurities such as silicon dioxide into silicates. So I given a series of reactions. Most of you have seen this diagram before in secondary school. In JC, you are not expected to draw it out, but you're expected to understand the process. Okay, you are given a series of reactions, 1, 2, 3, 4, 5. So there are 5 reactions. If you look through the list, you will realize that there are 3 exothermic reactions. The first one being the most exothermic. Okay, and then you also notice a series of endothermic delta S, or not endothermic, endergonic, or rather positive delta S. Okay, and you notice that 3 of them take on a relatively small value, these 3. Yeah, remember that this is in joules per mole per Kelvin. So if the value is really small, like less than 50, yeah, so that means that it's almost negligible. Okay, so let's look at the question. In the lower part of the furnace, the temperature must be hot enough to melt the iron. So state and explain which process is mainly responsible for raising the temperature of the furnace. Yeah, so over here, they are very explicit. Temperature must be very hot. So they ask you which reaction is mainly responsible. So only one reaction you are selecting. Simplest choice would be to choose the most exothermic one, which is reaction 1. Okay, so that will be the answer for part A. Just choose the most exothermic reaction. Okay, then for part B, the value of delta S for reaction 2 and 4 are much higher than the value of delta S for the other 3 reactions. Okay, so they are saying that these 2 are much higher. Let me change another color. Okay, so these 2 are much higher than the other 3. Ask you to suggest and explain the difference. Okay, so normally when they ask a question like this regarding delta S, the simplest way is to look at the change in the amount of gaseous molecules as the reaction proceeds. When I say as the reaction proceeds, we are looking at the reaction given to us. Okay, I repeat, the change in the number of moles of gaseous molecules as the reaction proceeds. So the reference point is the reaction given to us. Okay, so I'll look at the change here. So change in number of moles of gaseous molecule. I'll just put over here delta number of moles. Okay, the first one is actually 0. Yeah, because you start off with 1 mole of gaseous oxygen, you end up with 1 mole of gaseous CO2. The second one is +1. Yeah, so that explains why there's a huge increase, because there's an increase in number of moles of gaseous molecules from 1 to 2 as the reaction proceeds. The third one, 3 you get 3, so it's actually 0. The fourth one is also a +1, because at the start you have solids, you end up with a solid and gaseous CO2. Okay, the last one is 0 as well. Yeah, so the main explanation therefore for part B will be for reaction 2 and 4, there is an increase in the number of moles of gaseous molecules from 1 to 2 or from 0 to 1 as the reaction proceeds. So there's an increase in +1. So because of that, there are more ways to distribute the particles and their energies, yeah, as compared to the other 3 reactions, hence explaining why the value of the delta S is about 10 or more times greater. Okay, then for the other 3, I think you need to emphasize that there are no change in number of moles of gaseous molecules as the reaction proceeds, hence explaining the relatively small delta S. Okay, then finally we are looking at part C, that's the last part. Okay, so the question is the reduction of iron ore to metallic iron happens over a wide range of temperatures, typically between 500 and 1200 degrees Celsius. Calculate delta G for reaction 3, okay, at 500 degrees Celsius. So this should be quite straightforward. So again, we are looking at delta G is equals to delta H minus T delta S. Okay, so again, explain the effect on the spontaneity of this reaction if you increase it above 500 degrees Celsius. Okay, so we will assume that the delta H and delta S term do not vary appreciably with temperature. So that's the assumption that we have to make. Okay, so for reaction 3, delta H is negative 24.8. Okay, so that will be negative 24.8. Okay, minus T delta S, the temperature, we are looking at 500 degrees Celsius. So plus 273. Okay, and then what about the delta S? The delta S is given to us as 15.8. So 15.8 times 10 to the power minus 3. Okay, and then we do a quick punching of the calculator. We are going to get negative 37.0 kilojoules per mole. Okay, so they simply ask you to calculate the delta G. So you just quote the value. Then after that, they ask you to explain the effect of spontaneity of this reaction if you increase it above 500 degrees Celsius. You notice that the delta H is negative. Okay, the delta S is positive. Okay, so we should write positive here. Yeah, so as T increase, I expect the numerical magnitude of delta G to increase as well. Okay, so over here we expect because an increase in temperature will lead to an increase in the minus T delta S term. Okay, so maybe we can write out a better conclusion here. So when T increase, I expect the T delta S term to increase as well. So you expect that the delta G will become more negative. Okay, but over here, right, it will be a bit weird to say that the reaction become more spontaneous, because if a reaction is spontaneous, it is spontaneous. So there isn't a need to say that the reaction becomes more spontaneous. What you should say is the reaction become more negative and therefore more exergonic. I think learn to use this term, exergonic. Okay, so I repeat, do not say the reaction become more spontaneous, rather say that the reaction delta G become more negative and therefore the reaction become more exergonic. Okay, so that will be the end of our review to class exercise 5.